In this video, we are going to look at an example of two-dimensional flow, the flow down an inclined plane. So as always, before solving for this flow, we're going to draw what this flow looks like. So we have an inclined plane that is making an angle alpha with the horizontal, and there's fluid flowing down this inclined plane. So this is the fluid. And I'm going to define my axis in a way that's going to be helpful in solving for this problem. So this is going to be y, so that's the wall normal direction, and this is going to be x, the streamwise direction. The fluid flows in that direction. I'm also going to draw u in that direction, and just to exemplify what this flow, just to have an intuitive feel for what this flow does. Okay, so this flow looks like this, and of course this is a flow that is driven by gravity with the vector gravity pointing downwards like this. Okay, so the first thing, once we've drawn this, well, the next thing that we need to do is to write down the equations and the boundary conditions that we need to satisfy here. So this flow satisfied the, so this is, oh, sorry, this is a solid wall. So this fluid satisfies the Navier-Stokes equation, which reads rho du by dt plus u dot grad u equals minus grad, and I'm taking capital P, this is my total pressure, plus mu times the Laplacian of the velocity, this is my viscous forces, and of course the flow is driven by gravity, so I need to add rho g, okay? So that's the weight of fluid. This is to be solved together with the incompressibility constraint. Which stipulates that the divergence of the velocity has to be equal to 0. And we also need to provide boundary conditions for this flow, and the boundary conditions read as follows. So first of all, so at y, this is the wall normal direction, at y equals 0, and we're going to say that this is the fluid has we're at the surface of the fluid at y equals h. So at y equals 0, well, this is a solid wall, so we're going to apply no-slip boundary conditions. That is to say, we're going to say that the velocity is equally 0, okay? And then at y equals h, we have a free surface, so we're going to apply free surface boundary conditions. Which in this particular case here, we have a flat surface, stipulates that we should have continuity of the stresses, and that is to say that the normal vector times the dotted product with the stress tensor, the total stress tensor, has to be equal to, so this is the stresses within the fluid at this boundary, and that has to be equal to the stress from the air on the other side of the boundary, okay? And the air is only providing stress through the pressure, the atmospheric pressure, so I'm going to call this P atm, and this is carried by the normal direction again. Okay, so these are our boundary conditions, and we can, these stress boundary conditions can be expressed in more detail. So we can say that, so this is going to give me, we're in 2 dimensions here, x and y, so this is going to give me 2 scalar equations. One for the normal, so that's tau yy, that's the normal stress in the fluid, which is going to be equal to the normal stress in the air, which is just minus p atmospheric. And the second such stress equation is the one in which I dot to the right hand side with the tangential vector, which is x. So that's going to be the tangential stress tau yx, and that's going to be equal to the tangential stress in the air, and that tangential stress is 0 because n dot tau, n dot the tangential vector is 0. So that's going to be 0. And we can further write this out in more details using the components of velocity. In particular, tau yy is going to be minus the pressure in the fluid, okay, plus 2 mu dv, that's the velocity in the y direction, by dy, and that's going to be equal to minus p atmospheric. And the second equation here gives me that mu du by dy plus dv by dx with parentheses equals 0. So now that we have these boundary conditions and these equations, what we need to do is to non-dimensionalize them. So we are going to write down our non-dimensionalization. Starting with writing down the scaling quantities. And so for the velocity, we are just going to use a velocity scale capital U to non-dimensionalize our velocity. This is the dimensional velocity, this is the non-dimensional velocity in a sort of scale on capital U. For the positions, well, the only scale that we know in distances here is h. It's the height of fluid. So we're going to scale everything with h. Then for time, there's no need to introduce any other quantity because we can use h divided by u as a unit of time. And well, for the sake of defining a scaling quantity for the pressure, I'm just going to use rho u squared times, so that's just going to be capital P equals rho u squared capital P. These are capital P's in here. Okay, and that's going to give me my scaling quantities for my equations in boundary conditions. So I can now write down my Navier-Stokes equation. My Navier-Stokes equation becomes, by plugging this into these scaling quantities in here, we get rho u squared over h. Here we get rho u squared over h, so that factors out. Rho u squared over h times my right hand side, so du star by dt star plus u star dot grad star u star. That's my left hand side. And for my right hand side, I've got my pressure gradient here. That's going to be rho u squared over h. There's a minus sign coming in times nabla star p star. Here I've got my viscous terms where I am generating u over h star times Laplacian of u. And then here I've got rho g, so that's rho g. And I can write down g, rho g e g. So I can here write down that g is the acceleration of gravity times eg, where eg is the unit vector carrying that gravitational acceleration. Okay, so now that I've got this, I can divide everything by rho u squared over h, so that my left hand side doesn't have any prefactor. And if I do this, then my left hand side is du by dt plus u star dot grad star u star. And on my right hand side, the prefactor in front of the gradient of pressure simplifies. So I get minus the gradient of pressure. Here I'm going to have mu over rho uh, which is the inverse of the Reynolds number, okay, times the Laplacian of u star. Do not forget the star here, which indicate that we're talking about non-dimensional quantities. And my last term here will make the following term appear. That's going to be gh over u squared, and gh over u squared is the square of another number, another non-dimensional number, which is called the Froude number, Eg. So where here we've introduced the Reynolds number, which is rho uh over mu, and the Froude number, which is u over square root of gh. So these are just numbers, and you can just continue with the calculation with this, bearing in mind that this is a non-dimensional group, so it very likely has a non-dimensional number associated with it. Okay, so we can continue the calculation from here. We have this equation. There's one thing that just bothers us at the moment and it is the fact that the gravity isn't pointing in any very nice direction. So we need to convert this Eg into this Ey's and Ex's. And fortunately, it's not too difficult for us because we can see that Eg is, due to this angle alpha, it's going to have minus cos alpha in the y direction and sine alpha in the Ex direction. So what we have here is Eg equals, as I said, sine alpha Ex minus cos alpha Ey. Okay, and so, well, we can finish up writing the Navier-Stokes equation. I'm going to write down on the other side. The Navier-Stokes equation, finally, in this non-dimensional form, projected onto these axes, writes du star by dt star plus u dot grad with stars u star equals minus grad star p star plus 1 over the Reynolds number times Laplacian of u star. And then here I've got my 1 over Froude squared, so I've got plus 1 over Froude squared sine alpha in the Ex direction minus 1 over Froude squared cos alpha in the Ey direction. Okay, so this is our Navier-Stokes equation. The incompressibility constraint gets a u over h out when we non-dimensionalize it, so effectively it doesn't change much. It just becomes divergence of u star equals 0. The prefactor can be taken out of simplified and sent to the right hand side. And as far as the boundary conditions are concerned, so the non-dimensional boundary conditions, so for y equals 0, we get u star equals 0. That is the first one. And then for y star equals 1, which is y equals h, we have these two boundary conditions, which become p is non-dimensionalized by rho u squared, so we get rho u squared p star with a minus sign in front of it, plus 2 mu u over h times dv star over dy star equals minus p atmospheric times rho u squared. That's the first one. And the second one reads mu u over h, and I've got du star over dy star plus dv star over dx star equals 0. So these are these boundary conditions. And we can simplify them a little bit further, but I will not write them down just now because they will simplify. Okay, so these are this is our system. This is with our non-dimensional boundary conditions. And before we solve for it, we just need to make some hypotheses about the flow that we're looking at. So hypotheses. And these hypotheses, they're here to guide us into finding the simplest flow realization that can be supported by this configuration. We don't want to solve, this is a nonlinear problem, so we don't want to solve for all possible cases. Most of them are actually intractable analytically, but we just want to find the simplest flow, like we could do for plane Poiseuille flow or plane Couette flow or other simple flow configurations. So the hypotheses that we're going to make are designed to simplify these equations in such a way that we can find a very easily solvable flow analytically. So first of all, we're going to say that the flow is stationary. There is no need to add temporal complexity. We can imagine sheets of fluid flowing down that slope in a fairly regular and steady fashion. So that's one thing. Then what we're going to say is that the flow is one-dimensional. There's only velocity flowing down, okay? There is no velocity in the y direction. So we're going to say that this is a one-dimensional flow flowing along the wall. And the last hypothesis that we are going to make is to say that there are no variations of velocity in the streamwise direction. Okay, so everything is flowing, all particles found at the same distance from the wall are going to flow at the same speed. The only variation in the flow is going to happen due to this boundary condition. The no-slip boundary condition is going to cause variations in velocity in the direction perpendicular to the wall, in the direction, in the wall normal direction. So what we're going to say is that we're going to accept velocity variations only in the wall normal direction. And these hypotheses lead us to write that the flow can be simplified into u star as a function of y and not of x and not of time in the x direction and no other component in the other direction. So that is going to dramatically simplify our equations. So based on these hypotheses and this writing for the flow, we can, we can write down the Navier-Stokes equation in its component form in these two-dimensional problems. So the Navier-Stokes equation becomes, for the component u in the x direction, du by dt, which is 0, because u does not depend on t, plus u dot grad u, so that's going to be u du by dx, but u does not depend on x, so that's 0, plus v du by dy, well, but v equals 0, there's no component of velocity in the y direction, so that term is also 0, so the left-hand side is going to give us zeros. Then on the right-hand side we have minus the gradient of pressure, so that's minus dp star over dx star. Then I've got my Laplacian of velocity, and the velocity only depends on y, so I will get 1 over the Reynolds number times, sorry, d2 u star over dy star squared. And then in the x direction I've got this Froude plus 1 over Froude squared sine alpha. That's my first equation. Then in the second direction, what I get is, that's for v, that's in the y direction. V is 0, so there is nothing in the left-hand side. So my left-hand side is identically 0. I've got minus dp star over dy star. Then, well, v is 0, so there is no viscous forces on that component. And I've got here minus 1 over Froude squared cos alpha. Okay, so these are my Navier-Stokes equation. projected into these into these component forms. Now, if we look at the incompressibility constraint, what we can notice right away is that the left-hand side is automatically 0 because there's no variations of u in the x direction and there's no v anyway. What that means is that making this assumption here, u is only going in the x direction and only varying with the y direction. This assumption automatically satisfies the fact that the flow is incompressible. Okay, so these are our Navier-Stokes equation, and I can simplify these boundary conditions by writing that at y star equals 0, well, the velocity has to be 0, and at the same time at y star equals 1, that's my wall boundary condition. So you can see that now we can simplify things here, particularly this dv star by dy star is 0, and so what we get here is P star equals P atmospheric star. I forgot a star here. So what I did here is non-dimensionalizing the atmospheric pressure by rho u squared. So this P atmospheric star is also non-dimensional. Well, you can keep rho u squared if you want here, but then don't put the star. And then for this last equation, so first of all, mu u over h just simplifies because it's a prefactor and the right hand side is 0. But also u depends on y, so that's fine. I can keep this term, but this is identically 0, so I do not keep this. And what I get ultimately is du star by dy star equals 0 in this for this boundary condition. That essentially tells us that there is no friction. There's no tangential stress at the boundary. Okay? So these are our equations with the boundary conditions. So now we can just solve for these for the flow. The first thing that we can do here is look at the second equation. That's the simplest here. There's less terms, and particularly what we can write here is, so I'm going to write down here 1 and then 2, say that 1 leads to dp star by dy star equals minus 1 over the Froude number squared cos alpha. And so I can solve this and say that p star equals, it's going to be minus 1 over Froude squared cos alpha times y star, and there is a constant of integration, which I write k1. That constant of integration, fortunately for us, we have that boundary condition for the pressure. So we can essentially apply this boundary condition and solve for k1. And so by applying the boundary condition, we find that k1, so that's p at y equals 1 is p atmospheric. So we find that k1 is p atmospheric star plus 1 over the Froude number squared cos alpha. And in other words, my pressure writes as p star equals the atmospheric pressure, non-dimensionalized, plus 1 over the Froude number squared times cos alpha, and that's going to be 1 minus y star. Okay, so that will be my the analytical expression for the pressure. And what we can notice here, and which is going to be particularly interesting when we want to solve for 1, what we notice here is that p star does not depend on x, okay? Because, well, if we take the x derivative of this thing, it's necessarily 0. Y does not depend on x. These are numbers. And p atmospheric star, well, at the surface, p atmospheric does not depend on x, and therefore p atmospheric does not depend on x. So what we have is, because because P atmospheric does not depend on X, then it follows that dP star over dx star equals 0. Okay, and so that's going to simplify this term in equation 1. So now what we are left to do is, to solve equation 1, bearing in mind that this term is 0. And so we're going to solve for the velocity u star. So equation 1, now simplified in this fashion, gives us that we have d2u star over dy star squared is equal to minus the Reynolds number over the Froude number squared times sine alpha. Okay, so what I have done here is send this to the left hand side and multiplied by the Reynolds number, adding a minus sign in front. And so this equation solves pretty easily. So that gives us that u star is equal to minus the Reynolds number over twice the Froude number squared times sine alpha times y star squared plus a second constant of integration. We had a first one already when we solved for the pressure times y star plus K3. And so here we have boundary conditions to apply. Of course, we have two constants of integration, so we should have two boundary conditions to apply. We have one boundary condition at y equals 0, which is the velocity has to vanish, and the second boundary condition is this no stress boundary condition at the free surface. So applying the boundary condition to u equals at y equals 0, leads us to say that K3 equals 0, okay? And the other boundary condition, as we saw, is that at y star equals 1, du star by dy star equals 0. That says that there is no friction at this free surface. That essentially gives us here that minus the Reynolds number over the Froude number squared times sine alpha plus K2 equals 0. In other words, that's K2 equals the Reynolds number times over the Froude number squared times sine alpha. And so we can put that all into the velocity and write down the final solution of our problem, which is the Reynolds number over twice the Froude number squared times sine alpha, and I'm going to have 2y star minus y star squared in my parentheses. And so this is our velocity profile for the flow down an incline. And what you can see here is that this is a quadratic function. Of course, it's 0 at y equals 0, and it had to be maximum at y equals 1, y star equals 1. So we do have that, that quadratic profile, that parabolic profile here, that cuts here where there is no further increase at the point where the velocity is maximum, or in which there is no more velocity increase, because that free surface supports a free stress boundary condition, which we wrote here. Okay, so one last thing that we can do is to turn this into a dimensional solution. So we can write this in dimensional form. U star has to be u over capital U, so that's u, our dimensional u divided by capital U. Then I've got my Reynolds number, which is rho UH over mu divided by 2 if I want, times 1 over the Froude number squared, which I defined here. So that's going to be GH over U squared. gh over u squared, that's my fluid number squared, times sine alpha 2y over h minus y squared over h squared. And, well, I can just simplify this group, multiply everything by capital U, and what I get is U, my velocity, to be equal to rho g h squared over 2 mu sine alpha 2y over h minus y squared over h squared. In this video, we've solved analytically for a simple example of two-dimensional flow. This was the flow down an inclined plane, and this concludes this video on the flow down an inclined plane.